We're going to venture into the vast, silent expanse of the cosmos, where the greatest stories are written in the language of starlight and gravity. This is a journey that will take us from the familiar glow of our own galaxy to the unimaginable darkness that lies between them. It's a voyage not just across space and time, but into the very heart of mystery itself. Tonight, we're not just stargazers, we are detectives on a cosmic scale. We'll be exploring 5 of the most profound, most mind-blowing and still unsolved mysteries of the universe. These are the questions that keep astronomers up at night, the puzzles that challenge the very limits of our science and imagination. What holds the galaxies together? What is pushing them apart? Are we alone? These aren't just academic questions, they are fundamental to understanding our place in the grand cosmic ballet. So I ask you to come along with an open mind and a sense of wonder. Let's set aside what we think we know and embrace the thrill of the unknown together. Let's ponder these cosmic enigmas, not with the expectation of finding all the answers, but with the joy of asking the questions. The universe is waiting. Shall we begin? Imagine everything you can see. Your screen, the room you're in, the Earth, the sun, all the stars twinkling in the night sky. Now imagine that all of that, every planet, star, galaxy, and gas cloud, accounts for less than 5% of everything that exists. The rest, the overwhelming majority of the universe, is hidden from our view. A significant chunk of this invisible cosmos is what we call dark matter. It doesn't shine, it doesn't reflect light, it doesn't emit any radiation we can detect. It's utterly, profoundly dark. So how do we know it's even there? Gravity. We see its effects everywhere we look. We see galaxies spinning so fast that based on the matter we can see, they should have torn themselves apart, flinging their stars into the intergalactic void billions of years ago. Yet, they hold together. Something unseen, some invisible mass, is providing the extra gravitational glue. It's like watching a carousel spin impossibly fast without throwing anyone off. You'd have to conclude there are invisible seatbelts at work. That's dark matter, the universe's invisible seatbelt. Scientists are on a grand hunt for this elusive substance. We've built detectors deep underground shielded from cosmic rays, hoping to catch a fleeting glimpse of a dark matter particle bumping into an ordinary one. We've pointed our most powerful telescopes at the sky looking for subtle distortions in starlight caused by its gravity. Is it made of exotic particles we've yet to discover, like WIMPs or axions? Or is our understanding of gravity itself incomplete? Whatever the answer, discovering the true nature of dark matter will revolutionize our cosmic perspective. For most of the 20th century, we thought the universe was in a cosmic tug-of-war. Gravity, the force that pulls everything together, was battling against the outward momentum of the Big Bang. The big question was, who would win? Would gravity eventually halt the expansion and pull everything back together in a big crunch? Or would the expansion coast on forever? In the late 1990s, astronomers studying distant supernovae made a shocking discovery. Not only was the universe not slowing down, it was speeding up. Something is pushing the accelerator. The expansion of the universe is accelerating, with galaxies flying away from each other at an ever-increasing rate. To explain this cosmic anti-gravity, we've given it a name as mysterious as the phenomenon itself: dark energy. It seems to be a property of space itself, a kind of energy inherent in the vacuum. As more space is created through expansion, more of this energy comes into being, pushing everything apart even faster. It's a runaway effect, and it makes up nearly 70% of the energy density of the universe. What is this force? Is it Einstein's cosmological constant, a fudge factor he once called his biggest blunder, which might turn out to be his greatest prediction? Is it a new unknown energy field that permeates all of space, something we've called quintessence? We simply don't know. Understanding dark energy is one of the single most important goals in modern physics. Its ultimate nature will determine the final fate of our universe, whether it ends in a cold, dark, lonely expanse, with galaxies so far apart they can no longer see each other. Our galaxy, the Milky Way, is home to some 400 billion stars, and our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. The numbers are so vast they really defy human comprehension. With so many stars, a significant fraction of them must have planets, and a fraction of those planets must lie in the habitable zone where liquid water could exist. It seems statistically inevitable that life and even intelligent technological civilizations should have arisen countless times over the cosmic eons. And yet when we turn our radio telescopes to the heavens, we're met with a profound, deafening silence. This is the heart of the Fermi paradox, a question famously posed by physicist Enrico Fermi. If the galaxy should be teeming with life, where is everybody? Civilizations far older than our own should have had ample time to master interstellar travel, or at the very least send out signals, probes, or other evidence of their existence that would be impossible to miss. But we see nothing. No alien megastructures, no radio chatter, no starships flitting between the stars. The possible solutions to this paradox are as fascinating as they are unsettling. Perhaps we are truly alone, a unique accident in a sterile cosmos. Or maybe intelligent life is common, but it inevitably destroys itself before it can reach the stars. Could it be that they are out there, but deliberately hiding from us, observing us from afar, like we might observe animals in a nature preserve? Or is the universe so vast and the distances so great that we are simply too far apart in space and time to ever make contact? The silence of the universe speaks volumes, and honestly, we're still struggling to interpret what it's telling us. Of all the objects in the cosmic zoo, none capture the imagination or inspire more dread than a black hole. They are the ultimate abyss, the final victors in a battle with gravity. When a truly massive star dies, its core collapses under its own immense weight, crushing itself down to a point of infinite density, a singularity. Around this point is a boundary, a point of no return called the event horizon. Cross that threshold, and not even light, the fastest thing in the universe, can escape its gravitational pull. Our understanding of physics, rooted in Einstein's theory of general relativity, describes the gravitational effects of a black hole with stunning accuracy. We've even taken a picture of one's shadow. But relativity breaks down at the singularity itself. What actually happens in the heart of a black hole? Does matter truly get crushed to an infinitely small point? Or does quantum mechanics, the physics of the very small, intervene and create some new exotic state of matter? The laws of nature as we know them just cease to make sense. And then there's the information paradox. Quantum mechanics insists that information can never be truly destroyed, yet a black hole seems to be the ultimate information shredder. If you throw a book into a black hole, is the information contained in its pages lost forever? Stephen Hawking proposed that black holes slowly evaporate over eons, emitting what we now call Hawking radiation. But is this radiation random, or does it somehow carry the information of what fell in? The answer lies at the intersection of our two greatest theories of the universe, relativity and quantum mechanics, and we haven't found it yet. We have a remarkable story for how our universe came to be. We call it the Big Bang. About 13.8 billion years ago, everything we see, all matter, energy, space, and time, was compressed into an unimaginably hot, dense state. Then it began to expand and cool, allowing the universe as we know it to take shape. From the cosmic microwave background radiation, the faint afterglow of this primordial fireball, to the abundance of light elements, the evidence for the Big Bang is overwhelming. It's honestly one of science's greatest triumphs. But our story has a blank first page. The Big Bang Theory describes what happened from the first fractions of a second onward. It tells us nothing about the moment of creation itself, or what might have existed before it. What, or who, lit the fuse for the Big Bang? Was our universe born from the collapse of a previous universe? Did it emerge from a quantum fluctuation in some larger, timeless void? The question what came before the Big Bang might not even be the right question, as time itself may have begun at that moment. This is the ultimate mystery, the question that pushes science into the realm of philosophy. Some theories like eternal inflation suggest our Big Bang was just one of many, creating a multiverse of countless bubble universes, each with potentially different laws of physics. Could our universe be just a single, fortunate island in a vast cosmic ocean of possibilities? We stand at the very beginning of our timeline, looking back into a moment our physics cannot yet penetrate. It is the greatest once-upon-a-time story ever.